have Zhou telling us about energy and entropy of surface defects in 6 dimensions.
Okay, thank you so much. Thank you for the opportunity to speak, for the invitation to this nice place. It's my first time to Cambridge, so I'm getting very excited. Today I'm going to talk about two recent papers. One paper last year and one paper this year with my student, Ma Keyuan and Zixiao Huang. So the topic is surface defect in 6 dimensions. So we're going to discuss how surface defect contribute to the ground state energy and the entanglement entropy or Rayleigh entropy. In particular, we're interested in if there are universal behaviors for those contributions. Namely, compared with the 2-dimensional CFT, it's very known that in 2D CFT, the Rayleigh entropy or Casimir energy is completely fixed by the central charge. Now, if I'm a naive person, I can imagine that since I have a surface defect, the surface defect also preserves partial conformal symmetry. So if I stand in the surface defect, I might imagine that there could be similar universal behaviors for the surface defect contribution to the energy and entropy. That could also be universally determined by the so-called defect anomalies. So we already saw many discussions on this conformal anomaly, particularly this morning. Sergi also gave a very nice introduction about this anomaly and boundary contribution to anomalies. Here we're interested in this defect contribution to the anomalies. So for this audience, I think we don't need to advertise why defects are useful. So no matter you're a high energy physicist or condensed matter physicist or you're doing string theory, in many places the defects are extremely important to understand the physics. So if you ask me how to define the defect, in general, I don't think there's a sharp and universal definition because there are so many examples of different types of defects. So this is the usually I would say in quantum field theory, defects are usually defined by non-local operators or boundary conditions. Of course, but this don't cover every example, but cover many. So for example, defect can appear in the gauge theory. The defect can classify by their dimensions. For example, you have line defect or surface defect in gauge theory, a Wilson line or Wilson surface. And defect may also arise from a different point of view, slightly different. For example, you think about some lower dimensional degrees of freedom coupled with a higher dimensional theory or higher dimensional fields. Then your theory might be written as a higher dimensional theory and with this degrees of freedom located on this defect but coupled with each other. Okay. For instance, in this Lagrangian, I use the psi to denote the defect degrees of freedom. The couple with the Bloch field, which is phi. Okay. For example, in gauge theory, Wilson line can be written in this way. So you can imagine there is a internal fermions staying on this line. They couple with the Bloch gauge field. So after you integrate out this internal fermion, you recover this Wilson local operator. So you're happy because it's consistent with what we learned in the textbook about the Wilson loop. And because we know the Wilson loop can stay in the different representations, this essentially respected. It's reflected by how much fermion you can put on this line to span this Hilbert space. So from the simplest to more complicated, I would prefer this line. So if you ask me what is the simplest defect, maybe topological defect. So nowadays people use this topological defect to explore many interesting aspects of the symmetry. For example, the generalized symmetry, invertible, non-invertible symmetries. Then you go to slightly local ones, then you may think the conformal defect is the less trivial ones. And conformal defect usually appears as the fixed point of the defect RG, as we already saw from the morning's talk by Lawrence. you can discuss the general the RG located on the boundary, or in this case, you can discuss the RG located on the defect, so-called defect RG flow. There are many other examples. For example, interface, monodromy, or even entangling surface can be broadly viewed as defect. So, so this is called the defect landscape. It appears everywhere. So now, so defects come into the game, but if you originate from the Bootstrap community, then you can play with the, using Bootstrap, discuss the Bootstrap with defect. I believe Marco's talk will cover some aspect of this story. Then if you are originally come from some supersymmetry quantum field theory, in particular non-perturbative approach, then you might use something called a supersymmetry localization. Then you can also marry this supersymmetry localization with defect. For example, you can talk about if your theory has a defect, how to perform this localization calculation. Of course, you can also put the defect in the ADS-CFT context. For example, this picture shows that the square plane is a boundary, and imagine there is a block which is transverse to this plane. Then if you have a pair of quarks in your boundary field theory, it's just due to some stream worksheet in the ADS. Okay. So this is a Lorentz picture of a Euclidean circular Wilson loop in field theory and this holography duo, which is a stream worksheet. Yeah, there's some even interesting story here. For example, you can discuss about this this quark and anti-quark entanglement can be calculated, and it will be due to this horizon which emerges from this stream worksheet. Okay, this is some kind of defect version of ER equals to EPR. Okay, so it's very interesting if you insert defect in ADS-CFT. If you have more than one defect, then you can talk about how defect fuse. And you can even think about when the defect intersect with each other, how to solve it. Okay? There are many interesting questions. So as mentioned, if you restrict ourselves to conformal defect, you can do much more because symmetry break-in pattern is quite clear. So from these authors, we know this defect break part of the conformal symmetry is down to the part along this defect and the part transverse to this defect, namely the rotation symmetry. So the symmetry is broken. And you can work out this one-point function of the stress tensor in the presence of this defect. This is completely fixed by conformal symmetry and the conservations. This one-point function of the bulk stress tensor, for example, can be fixed up to some coefficient, small h. Okay. So we can discuss many others. For example, displacement operators. You can also try to explore the full bootstrap pattern with this defect. Okay? Some consistent relations, some positivities. But today we will be focused on a following question. So we focus on surface defect, which means the p equals to 2. The defect has dimension 2. So, as mentioned earlier, so for surface defect, analog to this 2D CFT wire anomaly, we have two more. Namely, we have anomaly coefficient B, D1, and D2. So as so this three coefficient appears in this defect contribution to the trace of the stress tensor. Okay. And then you can see. So the B is essentially the analog to the 2D CFT central charge C. And the D1 is the coefficient of the displacement operator two-point functions. And the D2 is the coefficient of the one-point function of the stress tensor. Since we already showed in previous page, as a small h, so small h will be proportional to D2. Okay? So in 2D CFT, we know in 2D CFT, we know there's a simple formula. For example, Rayleigh entropy is just determined by this central charge in this very universal form. Okay, if you can't compute a single interval Rayleigh entropy, you will get C over 6 1 over n plus 1, okay, as a logarithmic coefficient. And the cosmic energy of the 2D CFT will be minus c over 12 of the radius. Now I can ask, what happened for the surface defect? If I could compute surface defect contribution to the cosmic energy or Rayleigh entropy, then I might observe some similar pattern, right? Whether that contribution will be completely determined by this B central charge or D1 or D2 or some linear combination in general of these three anomaly coefficients. Yeah, so that's the question we want to ask. Of course, in general, this question is very challenging to answer. But as we will see, with the power of supersymmetry, we do found some compact formulas, namely some linear combinations of this anomaly coefficient completely fixed this defect contribution to the energy and also entropy. So what is the setup? So the setup is, the first question we'll ask is as follows. So imagine you have a defect. So to picture-wise this setup, let me use just a line. Later we will focus on surface, but let's think about this defect. So what we do is that we ask this, if we want to count this subregion entanglement A and A bar, we compute the entanglement entropy. That's the usual story to evaluate entanglement entropy. Now we want to do the calculation with this defect insertions. Okay. So after conformal transformation, this will become this one. Okay, this will become this one. So this is my subregion A. The left is the A bar, and the circular red line will be my defect. As you can see, the defect is intersected with the subregion A. Okay, so in this case, so what do we do? How to compute it? How to compute it? Actually, the calculation is straightforward. So we know without defect, the calculation can be done by using so-called replica trick. Now with defect, what you have to do is just you do the replica trick with this defect. That's it. Okay. So what is the replica trick in this picture? The replica trick means we cut along this subregion A, we glue many copies cyclically. Okay, we evaluate the partition function and then the Rayleigh entropy, and then take the n goes to 1. We get the entanglement entropy. Now with this defect, you have to do the replica trick, because if you cut in this way, you basically also cut this defect. Okay, but eventually you are gluing everything together. But you can imagine that when you perform the replica trick, you also replicate this defect. Okay, as you can clearly see from this picture. Therefore, so finally, the defect contribution to the entanglement entropy should be contributed by these two terms. So I just use this formula. This is the usual entanglement entropy formula. Without defect here will be some log partition function. Now with defect, this should be replaced by this log expectation value of this defect. Okay. Then eventually you take n equals to 1, or n goes to 1. Then you get two terms. Just evaluate this one. You immediately get two terms. First term is the log W itself. What about the second term? The second term is coming because you take a derivative with regard to the replica number n. Is equivalent to you are writing this tau component of the metric. Okay. Then the response will be the stress tensor. So it's not surprising. The second term is the 1-point function of the stress tensor, and you have to integrate that over the whole space. So this is the 1-point function in the presence of the defect. Okay, in the presence of the defect. When we know this is non-trivial. Without defect, this might be trivial, but with defect, this is non-trivial. Okay, so you have to do this integral, and then you add up these two. You get the final result. Okay, this is the setup or the calculation approach. Now, at the start, we want to focus on the previous calculation was actually done already by this to local with Marcina in 2013. So we want to develop the calculation following that approach, but now for the surface defect. Then you ask me, what is the simplest example for the surface defect? Okay, what is the simplest surface defect? Now, arguably, the surface, simply the surface defect will be given, you have to go to 6 dimensions, okay? So why? It's simple dimension counting. Because in 6D, the scalar can carry dimension 2. Then you take a scalar operator, integrate over surface, you get the surface defect, okay? This is the simplest one, and this is a conformal one. If the box theory is free, then everything is calculable, okay? Yeah, so this is the simplest one. Similarly, you have the surface defect for the two-form fields. Okay, and this is the action for the two-form fields. Okay, indeed, then people already computed this 2H coefficient. We know H is proportional to D2 central charge. Okay. So H, this is the value. These are values for the scalar surface defect and the B field, the surface defect. You get these numbers. Okay. So as said, we want to count this surface defect contribution to entanglement. Okay. So what is the setup again? So we put the surface defect here. So this is my time. This is my time slice. So this is the blue circle inside. The blue circle is some sphere, and inside the region is some ball region, which is my subregion. Okay. So I want to compute the subregion entanglement entropy for this subregion. Now with this surface defect insertions this way. So for symmetry reason, I put everything in the most symmetric way. Namely, the surface defect pass through this origin. Okay. Then this is the setup. Now it's a little bit scary. There's a few stuff you have to calculate. If you want to develop the calculation, but there's a trick. If everything is conformal, then you can conformal transform. So this is the standard story, but the so-called Castelli-Weirton-Myers mapping. You can map this original flat space entanglement entropy to some hyperbolic space partition functions, thermal partition functions. Namely, you just do this map. Then after this map, you have a tau circle, which is a replica circle, and you have a hyperbolic space. Now you ask, where is the defect after this map? So after this map, if you track your defect, then you realize your surface defect is wrapped on this tau circle and also occupy this radial direction of the hyperbolic space. Okay. So this is one dimension, this is one dimension, so plus we have 2 dimensions. So this is the surface defect appeared after this conformal map. Then you can calculate for this geometry, right? For example, you can do the calculation for free fields. So since it's 6-dimensional free fields, if I use the Haidt-Kerner approach as advertised by Professors Solodukin, Smolin, so just find from literatures this Kerner result for the H5 and also for S1, and then you multiply these two, do some integral, you get the Green function of propagators. This is the propagator in 6 dimensions. Now it's not difficult to convince yourself in order to evaluate the expectation value of this very simple surface defect as defined here. The only thing you have to do is just take this 6-dimensional bulk propagator, let this propagator, 2 endpoints of the propagator integrate over the surface defect. That's it. Okay. Why? Because this is the simplest surface defect. You do Taylor expansion. You calculate this one in the path integral. You realize the only thing you have to do is just this integral of the propagator, but with 2 endpoints over this surface defect. That's it. Now, if you naively do this calculation, of course, it's divergent, but you carefully deal with this divergent term. You get this final result. Then you realize the final result in this case is 0. So then, do we think this is the final answer? I mean, we do this standard calculation, we get some result which is 0. 0 means this defect expectation value is 0. Is that all? No, in this case, there is some additional contribution we missed, which is the boundary term. So let me explain why. So additional term could appear on the boundary of H5. So the boundary over H5 is nothing but the entangling surface. Okay. In the canonical calculation of this entanglement entropy, we have a geometry of a cone. There is a tip of a cone, which is singular. Okay. So what do we do? The way is first resolve this singular point, and then take the limit. Okay, take the singular limit. So that's the standard procedure. So usually that contribution coming from the tip of the cone does not affect the bulk, the universal piece of the bulk entanglement entropy or ring entropy. It just doesn't matter because it contributes a finite piece. But with this defect, it's not trivial. Okay, why? Let's calculate it. So with this defect, so that term is essentially contributed by this conformal coupling, which is R phi squared. Okay, so because apart from the tip of the cone, all other curvature is trivial. So usually we throw it away with R equal to 0. But now if you resolve the cone, then it brings in some non-trivial curvature. So this R phi squared term is non-trivial. Now, not only that, now in my setup, there will be additional defect here, inserted here. Okay, so when you resolve this cone, which is essentially this blue circle, okay, the tip of the cone, which is the blue circle, then that phi square operator will have non-trivial expectation value, this double bracket, because of the presence of the defect. Okay, so you have to calculate this one. So you calculate this one, you find that there's a non-trivial contribution to the entropy, which is this one. So you compute this one carefully, you get some minus 1 over 10 pi, again logarithmic term. So we found that there are a non-trivial logarithmic term, which is the same level of the logarithmic universal terms we want to claim for the surface defect. So we cannot ignore this one. Okay, so this is quite a non-trivial piece. So now you see why there's a negative, because in general the defect contribution to entanglement entropy has not to be positive. So it's a negative number now. So it's negative. So how do we know this is correct?
Sorry.
Yes.
Can I ask you what that ln the epsilon? Just the parameters in the log. What is ln? What is epsilon?
Element.
Yeah, just in the log.
What is epsilon?
Yeah,
Epsilon is a cutoff.
Epsilon, what is that? Just
Yes, epsilon is a cutoff. The cutoff is associated with if you have a surface defect, you have entangling surface, because we have a divergence in general. So the cutoff comes from some intersection here.
Okay.
Yeah, some intersection here. If you do the integral, you realize that there is a divergent piece. You have to put a cutoff. Then you carefully do the integral, you have a log, which is the universal term. So how do we know this is the correct? Very fortunately, there's already a known formula appeared, or I think worked out by Andy and the collaborators in 2018. They proposed that the defect contribution, in particular, surface defect contribution to entanglement entropy is determined by central charge in this way. Okay, this way. So let's test the consistency. So if you plug in the data, so you find that this is S contribution is what we contribute for free fields, and the sample is the defect, and this is the D2, and in this case B central charge is 0. Then you plug in, you find that indeed pass this test. Okay, so
because
yes.
you introduce a defect of the root y, so on this theory for the defect integrity should be larger than 0.
In this case, it's a surface, it's also a line.
I say that it's unnecessary S should be larger than 0 because it's not the usual integral interface, right? Because you introduce defect, so I expect it's equal to some King potential layer, then either can be negative for the defect integral interface. I guess that.
No, I think it was proved or pointed out by Nishioka and some papers. Defect contribution to entanglement entropy in general is not positive.
Yeah, so it's not the usual integral interface.
Depends on what you mean by usual. Here, the definition will just
because
be.
At least if it's a usual integral, the first term should be larger than 0. Because the first term will not be affected by any regression. So it has a meaning. So
here, the definition is we use the entanglement entropy with the defect and subtract the entanglement entropy without defect. And we call the defect contribution to entanglement entropy.
Yeah, sure. So,
yeah,
so
which is not necessary to be positive.
Yeah, so I just say it's not a conventional integral term because you introduce a defect in it.
Okay. Yeah. So I believe this is this setup of calculation is correct. Then what can we do more? So we just now jump a little bit. Of course, we also checked for two-form fields. But, now we want to go to this so-called 2-0 free theory, which is the string community. People are interested. This is the so famous 6-dimensional 2-0 theory, which is the maximum superconformal theory, and also appears as a one-volume theory for M5 branes. So in general, it's complicated. For the interacting theories, we don't know how to write down the action, for example. And yeah, there are many mysterious things. But at least in free theory context, this is a little trivial. You can just count and multiplet. So the free multiplet includes the 5 real scalars, 2 wireframes, and the 2-form field with the self-dual strings. Okay. So what can we do is that just following the definition of the BPS version line in the n equals 4 super YAMLs. So in this case, we just combine these self-dual 2-form fields and these scalars, 5 scalars. See, then you can put together to define some surface operator. Okay, something like this. Then you can ask for this kind of object, what will be the defect contribution to Rayleigh entropy? And the answer is just the sum of these two, because it's the free fields. Okay, you can just sum them together, and this half comes from the self-dual. So her self-duality reduced the degrees of freedom by half. Okay, so you get -1/10 pi. By the way, the common remark that will be here, compare with this. Formula in this explicit example, we claimed slightly more than that. We claim that this result is the defect contribution for Rayleigh entropy, not only entanglement entropy, but for Rayleigh entropy. Okay, why? Because we performed this the calculation use this Haidt kernel, and we do the replica trick. Okay, and we found it's just a constant. There's no Rayleigh index dependence. Okay. So it's just a constant, and also equals to entanglement entropy. Yeah, so this is the result for the free. Now, as said, if the theory is interacting, we don't know how to do calculation, because we don't know how to write down the action. We don't know how to do the event localization. Because we don't have action. Okay, and it's very challenging. But at least we can do something more, which we can use the ADS-FT. So in the original ADS-FT paper, already being conjectured, this theory will be holographically due to M theory on this ADS7 times S4. This will be the bulk metric, and this is the field content. And luckily, we do know for the surface operator in this 2-0 theory, if the surface operator in the fundamental representation, it will be due to M2 brane. Okay. So we can evaluate this M2 brane action from holography. Okay.
Did you say M2 branes or a single M2?
A single M2 brane.
Single.
Yeah. Yeah. So you can do it this way. As I said, we want to ask the question initially: what is the surface defect contribution to the Rayleigh entropy? But if you talk about the Rayleigh entropy, in general, Rayleigh entropy involves some replica trick. The replica trick will break all the supersymmetry. Okay. So if you want to really seek for some original Rayleigh entropy, supersymmetry must be broken. Then really nothing you can compute, okay, for interacting 6D theory. Okay. So we have to preserve the supersymmetry. So we have to twist a little bit in order to push the calculation. So what can we do is as follows. We put the 6-dimensional theory on this S1 times H5. Okay. Why this finally manifold? Because this manifold is precisely the manifold coming from this conformal map. Okay. So we want to talk about the theory, 6D theory on this manifold. Now the point is, if beta is not 2 pi, okay, when you do replica trick, you tune in beta. When beta is not 2 pi, this manifold break all the supersymmetry. In order to preserve supersymmetry, you have to use this R symmetry background field to twist this geometry. Okay? So you carefully check that there is a way, actually a very simple way, to twist this geometry to preserve supersymmetry. For example, you can try to work out the Keenan spinor equations. you realize the background field is something proportional to n minus 1. N is the Rayleigh index n. Okay. So then after this twisting, you can get something called supersymmetric Rayleigh entropy. It was initially introduced by Lishoka, Yakov, and later we just following the idea and compute this object in 4 dimensions, also 6 dimensions. Okay. So in particular, in 6 dimensions, there's a nice and simple result for this quantity after twisting. Okay. So after you twist, you get this so-called twisted Rayleigh entropy. It's just a cubic polynomial. It's a simple cubic polynomial. The variable is the 1 over n. Okay, it's just the cubic polynomial of 1 over n. Then you can expand it this way. There are 4 coefficients. Okay, S0, S1, S2, S3. So these 4 coefficients completely determined by the 'T Hopf anomalies. Okay. We do know the A form 'T Hopf anomaly or anomaly polynomial for this 6D series. This has already been worked out by people. For example, in this nice paper by Tachikawa and collaborators. So we found, a couple of years ago, we found that this anomaly coefficient completely fixed this twisted Rayleigh entropy. This is without defect. As said, why we care this? Because if you don't twist the Rayleigh entropy in general, supersymmetry is broken. Yeah. No calculation you can do. Now we ask a further question. What is the defect contribution to the Rayleigh entropy? So better to ask what is the defect contribution to this twisted one, because twisted one preserves supersymmetry. Okay. So luckily you can define some defect contribution to this twisted object, also preserve some supersymmetry. Then there's a hope this contribution to this kind of entropy, particular entropy, could be simply determined by the anomaly, by the defect anomaly. Yeah, that's the question. So this is a holography calculation to justify the previous formula. Yeah, just to try to advertise this kind of formulas to you, because this formula is simple and it can pass through all the tests, for example, holography. So we know this 6-dimensional 200, if you put on S1 times the H5, there's a simple holography due, which is so-called hyperbolic black hole, which is a 7-dimensional black hole. Okay. Is a 2-charge black hole because there's a 2 katon of the SO5 R symmetry for this 6D series. So there's a simple solution. So you can compute from this solution the twisted Rayleigh entropy. You found this result. Then you can immediately check this result. In particular, all these coefficients precisely agree with the previous formula. Yeah. So actually, this formula is claimed to be true for any 6D SFT. Any 6-dimensional superconformal field theory with 1-0 supersymmetry. So that's good, but we want to ask more about this defect contribution. So what is the surface defect contribution to this twisted Rayleigh entropy? As said, we can do the M2 brane calculation, right? So you have the background geometry, now you just add this M2 branes. So the boundary of the M2 brane will be the 2 directions. One is the tau circle, right? Another is the radial of the hyperbolic space. That's the boundary of the M2 brane. Now M2 brane has additional bulk extension. So you evaluated it. You evaluated this on-share action of this M2 branes. You get something like this. Okay. Then you computed this. You get the large N result for this defect contribution to the twisted Rayleigh entropy, which is a very simple result. Looks like this one. So gamma is 1 over n. N is Rayleigh index. So we saw from here, the contribution is a linear function of gamma, and is linear proportional to n. It's linear with n. Okay, this is what we expect because this is a defect contribution. It's linear to n. And one more nice structure is this is just the linear function of this gamma. Okay. Then if you what is R1, R2? R1, R2 is the parameterized background field because we have 2 katons for the SO5 R symmetry. You can turn on 2 independent background fields. So how much you have 2 independent turning on, then then you have some weight. Okay, there's a weight factor which is called R1, R2. So R1 plus R2 equals 1. If you put them equal, which means R1 equals to R2 equals to half, then you get this result. Okay, so that's is it clear formula? Okay, but we want to
Can I have a question here?
Yes.
Before, all the formulas in the non-supersymmetric case did not depend on n. Like at some point you do the differential with respect to n, and then you.
But the point is, after you twist, there could be a dependence.
Okay. So the twist generates this dependence.
That's
Okay,
right.
thank you.
Okay. So, but we want to do something more because now we somehow know the free, partially know the free field calculation and the holography large n calculation. But what happened for all the intermediate region, or any n, okay, or any coupling? Is it possible to conjecture some formula valid for any n and any coupling? Yeah, we try to do so. The conjecture formula is as follows. So the formula goes as follows. It says that the defect contribution to the entropy is controlled by the 2b minus d2 as the overall factor. Okay. So, and the other structure very similar to the previous large n result is, for example, is a linear function of gamma. Gamma is 1 over n, and there is a R1, R2. Okay. And the point is the anomaly dependence is controlled by 2b minus d2. Okay, so where we get this one? How do we know this is correct? Okay, so in the remaining time, I'm just trying to justify this conjecture formula step by step. Okay, step by step. So first of all, inspired by the large n calculation, we conjecture the compact formula is still a linear function of gamma. Okay, of course this is a big assumption, but as we will see, this is correct. Okay, so that's the assumption. And then if you assume this is a linear function of gamma, then in order to obtain the full result, you just need to determine the two coefficients. Okay, it's a linear function. So let's do one by one. Okay, first let's determine these leading coefficients of the gamma, or 1 over n. So very fortunately, that coefficient is also connected to something called twisted cosmic energy, or supersymmetry cosmic energy. Okay, why? Because there's for the geometry, where it's a pure geometric reason, right? So if you put the theory on the S5 times the H1, which is conformally equivalent to the previous manifold, which is S1 times the H5. Okay, you can easily check these two geometry are just conformally equivalent. Okay, so I can switch to this manifold. So if you switch to this manifold, you can already observe this is almost the geometry prepared for the cosmic energy, right? Because H1 is the very, very long circle, okay? You can imagine that way, or it's infinite. And then you have S1. So the particular function of this geometry should give you cosmic energy. And the previous Rayleigh index somehow related to here is the squashed S5 sphere, the squashing parameter. So the point is, if you know how to calculate this supersymmetric cosmic energy on this manifold, you take the squashing parameter to extreme. You take the squashing goes to 0, for example, okay, very extremely squashed. Then this is equivalent to say on the Rayleigh entropy manifold, you take the temperature goes to very high, which is nothing but this leading coefficient, okay, which means n goes to 0, right? So gamma is very large, so you can extract this leading coefficient. Indeed, we will say this coefficient is precisely reproduced from the supersymmetry cosmic energy. Without defect, everything is very clear. The connection, okay, that's already clarified like about 10 years ago. But now we want to do the with defect. Okay. Then you realize the with defect is story still happens. Okay, still happens. So you can check that. And very luckily, we know how to calculate this surface defect contribution to the supersymmetry cosmic energy. Then we can use this as that result, and we can justify this leading coefficient. But that's just the only. This is just the leading coefficient. But what about the constant piece? Okay. What about the constant? By the way, the defect supersymmetry cosmic energy, or defect contribution to the supersymmetry cosmic energy, can be justified by many independent calculations. So we believe that result is also correct. For example, you can compute it from localization, Yeah, we will explain why. Previously, I said the 6D theory does not allow any supersymmetry localization, but why in this case allowed? Yeah, we will explain. Here, localization essentially means 5-dimensional localization calculation. Okay, and it can also be justified by some equivalent integral of the anomaly polynomials. Okay, this is a very standard calculation. So we do know the anomaly polynomial for the surface defects. So we try to perform the equivalent integral. We got this precisely the same result for the defect contribution to supersymmetric cosmic energy agrees with this localization result. Yeah, we will discuss later. And then, yeah, it's justified this defect contribution to the supersymmetric cosmic energy. So use that result, as said, we can justify the leading coefficient. Now, what about the constant? Now, at this moment, let's just simply take the constant should be some linear shift of B over 3 by D2. What does this mean? This means that previously we know without any supersymmetry, the surface defect contribution to entanglement entropy is in this way, right? So observe this formula. This is some B over 3 shifted by some D2, okay, with some coefficient, okay? So we still think in this case with supersymmetry, it should be shifted by something proportional to D2 for the B over 3, okay? Then you can just try to fit with the data, right? You have the holographic data, for example, then you can determine the coefficient. But of course, you might think this assumption is a big assumption. Yes, at this moment I agree, but later we will justify the compact formula is indeed correct. So I'm trying to explain this approach, just trying to quickly get this closed formula, okay? Then you use this approach, you indeed get this closed formula, okay? It goes in this way. Now, how much time do we still have? 15 minutes, very good. So let's now go step by step, try to just how to see first derive the defect contribution to the supersymmetric cosmic energy. So what is the supersymmetric cosmic energy? Supersymmetric cosmic energy, by definition, is some supersymmetry twist for the cosmic energy. So here, the cosmic energy means we have a sphere. We have a sphere in this 6D theory. We have S1 times S5, okay? And the S1, learns of the S1 is the beta. So we take a beta goes to infinity. This is the lower temperature limit. In that limit, we take a derivative for the log z, okay? Derivative with respect to beta, we get cosmic energy. Okay? That's our definition here, the cosmic energy. So it's the cosmic energy associated with the sphere, which you quantize your theory. Now, as mentioned before, in this setup, this 6-dimensional cosmic energy is related to the 5-dimensional partition function on the 5 sphere. And the 5-dimensional partition function can be computed from the supersymmetry localization. Okay, that's already known. In particular, in this paper, Bobav, Bullimore, and Kim, 2015, they beautifully calculated this supersymmetry cosmic energy for the 6D theory, but without defect. Okay. The point is as follows: the temperature for the 6D theory is related to the coupling of the 5-dimensional Yang-Mills. Okay. Okay. So why? Because yeah, you can imagine this is from 6-dimensional point of view. You put the theory on this S1 times S5, and then from 5-dimensional point of view, you get some maximum supersymmetric Yang-Mills, okay, Yang-Mills, and then by some dimensional analysis, you can see that beta is proportional to the Yang-Mills square. Then the calculation of the large beta it just reduced to the calculation of the Yang-Mills square goes to very large from the 5-dimensional point of view. You can do that limit in the localization calculation. Then you simply get the matrix integral in this form. Then you can use the cell point method to try to solve this matrix model. Then you eventually get this beta EC. EC is the cosmic energy. You get this result. Okay? This is n times n squared minus 1. This sigma is the chemical potential for the R symmetry, and the omega is the chemical potential for the rotation. Okay, So you get this result. So this result is beautifully consistent with the result which you get from the equivalent integral from the Olomouc polynomial. Okay, very nicely consistent. Yeah, we will use that even in the case of the defect. Okay. Now with the defect, you can push this localization calculation. Why? Because the surface defect in the 6D wraps both S1 and one circle inside this S5. Now, from 5-dimensional point of view, you just reduce to some Wilson line, okay? Wilson line, because 5D series on the S5. So for that localization calculation, already you can do it, okay? You can do that localization. For example, that contribution from this Wilson line just given by some insertions, okay? Some new insertions in this matrix integral. Now you can just go through it, calculate this matrix integral. Yeah, then for symmetrical representation, for example, you get this result. For the anti-symmetrical representation, you get this result. So, yeah, so this is all for the 2-0 in the A-type Lie algebra. Right? We know the 6D2-0 series is classified by ADE, different ADE types. And for A-type Lie algebra, the surface defect can stay in different representations. Now, this is the result for the two particular representations. Yeah, you can obtain this result from this matrix integral. You can also you get some result, right? This is the result is essentially the defect contribution to cosmic energy. I normalized all the bulk contributions. Okay, I only pick up the defect contributions to the ground state energy. Then I get this one. So how do I know this is correct? This is, you can check consistent with the equivalent integral from Olomouc polynomials. So the Olomouc polynomials, these people already obtained for the surface defect in the 2-0 series. Okay, it's a 4 form. It's I4. There are 4 terms. Okay, because this is the 4 independent R symmetry. Okay, R symmetries. So you have this Olomouc polynomial. Now you do the equivalent integral for this Olomouc polynomial carefully. Then you obtain the result. So learn from the bulk connection between the equivalent integral and the cosmic energy. We can generalize it to this case of the defect. So you get some result looks like this. Then you identify the 2-dimensional parameter and the 6-dimensional parameter. You can rewrite the cosmic energy just in terms of this recently found formulas. Recently, for this type of surface defect, I think many people are here. It's a nice paper pointing out this B central charge and the D2 central charge are completely fixed by this representation of the surface defect and also the wire factors. So lambda is the highest weight of the representations for the surface defect, and rho is the wire vector. Okay, this is the inner product in the Lie algebra. So you just write the cosmic energy in terms of this B and the D2. Then you get some compact formula goes in this way. Okay, there are 2 terms. Okay, 2 terms going this way. So in particular, you can check in the so-called carrier algebra limit. This is reduced to the -1/12 omega 3 D2. So in the carrier algebra limit, this cosmic energy, defect contribution to the cosmic energy, is completely controlled by this D2 central charge. But in general, this is not true. In general, is more complicated. It's determined in this way. So now we use this, take use of this cosmic energy result. Okay, this cosmic energy result, you can easily justify the previous entropy result. Okay, you find that in the extreme squash limit, indeed, this term shows up. This 2b minus d2, second term shows up. Okay, the first term suppressed, the second term shows up. So you get 2b minus d2, and then actually we can put additional consistent check because previously we just used some very sloopy argument to fix the constant term. Okay, now we can perform a more serious check. The check goes as follows. So previously without defect, there is an additional connection between energy and entropy in this case. Okay, so I didn't show you details in the slides, but I can explain. So the connection goes as follows. You can try to blow up this energy, this cosmic energy, by adding one more omega, okay, in this BPS equation. There's a BPS equation connect omega and sigma. Okay, these are symmetry chemical potential and the rotation chemical potentials. So if you add one more omega, and then you take one of the omega is 1 over n, or other set to 1, then you can evaluate this entropy from this energy. So you beautifully recover all the entropies from the cosmic energy. Now we also test in this defect contribution. We indeed found these two formulas precisely connected in that way. Okay, so we believe this result is correct. Yeah, I finished a few minutes in advance. So let's conclude. So we propose the closed formula for defect contribution to the super Riemann entropy as well as the super symmetric cosmic energy in terms of defect conformal anomalies. The future question you can ask is, you talk about the ground state energy, you talk about the Riemann entropy, but what happens in this opposite temperature limit, which is the high temperature limit? Is also very well known in the 2D CFT. We have a beautifully Cardi formula. Okay, in the Cardi region, which is the high temperature limit, the behavior is also controlled by the central charge. What happened for this surface defect at this time? Okay, this is a still open question. Okay. Maybe some of the audience have some progress, but at least to me, it's still quite open. We don't know whether such kind of formula exists or not. First of all, okay. Yeah, so I think it's a very interesting question. Yeah. Can we ask, in particular for the surface defect, what if you take the high temperature limit? Okay, can you extract something like Cardi formula or defect Cardi formulas? And could there be some bounds on these defect anomalies? Okay, because now you get some defect contribution to entropies. So from quantum information, usually when we have a compact formula for entropy, we can play with some inequalities. Okay, for example, Shannon entropy. Okay, there are inequalities or Riemann entropies. There are inequalities. Maybe from this entropy result, we can get some bounds on these defect anomalies. That's also an interesting question. And a more practical question will be just to try to extend this formula to more general theory and different co-dimension defects. Okay. For example, what about the 1-0 series? What about 1-0 series? Yeah, we believe there is also a similar formula exists for 1-0. We didn't really achieve that. You can also talk about the different higher co-dimension defects. For example, co-dimension 2. In this box theory, if this box theory is 6 dimensions, then you can discuss the co-dimension 2 defects, which is 4-dimensional defects. Okay. You can also ask what happens for the glucose weight in 4 dimensions, 4-dimension box series. Okay. This is also a famous surface defect, where this class of surface defect also obey or satisfy those universal formulas. Namely, if you could be able to compute this defect contribution to energy and entropy, would that be controlled completely by the anomaly? We don't know yet. Okay, I think these are all interesting questions. Okay, thank you so much.
Thank you for the nice talk. Are there questions?
So, you mostly talked about entanglement entropy, about an entanglement surface that is symmetric intersects the defect. So there was some recent work in 2D in particular by Hiroshi, Kuzuki, Monkey, and I'm missing an author, Karch, about intervals which are asymmetric, in particular entanglement entropy of one side with respect to the other. So the entanglement surface ends on the defect itself, with some claim of some universal bound between this and some energy quantity. So is there something similar that can be computed in higher dimension in a supersymmetric setting for this?
That's a good question. First of all, I have to admit I'm not familiar with that detailed contents of that paper. Yeah. So yeah, the setup is quite different.
Yeah.
And yeah, it's an interesting question. I'm not aware of details in that paper.
Yeah, I can tell you.
Yeah, sure. We can discuss.
Any more questions? Chris?
Sorry, I think I'm getting sleepy, but can you say again why you'd expect this relation between the super Renyi entropy and the supersymmetric Casimir energy? That there is this thing of this large beta limit. There's some geometric intuition.
Good. Yeah, I can explain with chops. Okay. Yeah, there's a connection because Renyi entropy is defined as we saw. It's defined on this geometry. Okay. And this is conformally equivalent to H1 and S5. Okay? You can easily check this is true. You just extract a wire factor. Yeah, you can map between these two methods. So here, almost by definition, you can see this manifold, if you could compute the partition function on this one, you get cosmic energy, right? Because this is the infinite long circle, okay?
I see.
Right?
Okay.
So this is defined energy and this is defined entropy. So it's just a geometrical reason.
It doesn't matter that the H1 has a boundary?
Yeah, it doesn't matter because cosmic energy is just controlled by this one. It's the bounce energy for the state quantized on this as well. Of course, this has to be very large, right? But usually, when we define the cosmic energy, we don't. We just take a beta goes to infinity. Yeah, we disregard this circle, right?
Sorry, can you quickly say again why supersymmetry is important to find this?
Good. So, because replica trick in general break all the supersymmetry. And the point is, without the supersymmetry in 6D, you cannot do any calculation so far by the knowledge. Maybe you can do bootstrap a little bit. I think most of the result is with supersymmetry. We want to preserve supersymmetry, then we twist. The point is, yeah, you can easily check. For example, you can check on a sphere. If I have a sphere, for example, S6, you can do some conical deformation, okay? You can choose a circle and try to replicate. Replicate means I change it to 2 pi to some 2 pi plus something, okay, or minus something. You can see Kenny spinner does not exist anymore if you do this deformation. Yeah.
Good? No? Okay, any other questions? Okay, if not, let's thank the speaker again.